Hi, a very good morning to one and all. I'm Supriya Bhide, and I'm a PhD student under Professor Khedker and Dr. Pritam Gharat. So I'll be presenting today's talk on a correspondence between five function placement in classical SSA and reaching definitions analysis. So let's first quickly take a look at SSA. We've already taken a look at it before. So SSA in short is static single assignment. Every variable has exactly one static definition and exactly one definition reaches the use of any variable. So we have a control flow graph on the left uh, and we have its SSA form on the right. As we can see, every variable has been renamed into a unique every definition has been given a renaming in order to make it unique. However, we notice that at node 3, a definition of A with the value of 400, for example, here reaches node 5, and a value of A with this particular value reaches node 5. So in order to take care of this situation, we insert a phi function. So let's look, so since we're talking about context sensitive SSA, we looked about it in the previous talk. So context sensitive SSA works at the interprocedural level. And currently we do not have an optimal phi function placement algorithm for cost SSA at the interprocedural level. So let's look at how the phi placement takes in classical SSA. So classical SSA works at the intraprocedural level and it is based on dominance frontiers. So let's take a quick look at a few definitions. So this is what dominance is. So I'll just name the nodes. So it says that node 2 dominates node 3 if every path from start to node 3 passes through node 2. However, node 3 would not dominate node 5 because not every path from start to node 5 passes through node 3. And the dominators have been given here. So dominance, the speciality of dominance is that a node can also dominate itself. We now come to the notion of strict dominance. Strict dominance is just like dominance. However, it says that a node cannot strictly dominate itself. That's the only difference. So with these definitions at hand, we now come to the notion of dominance frontier. So dominance frontier basically, in simple terms, is the first node at just before which the dominance of a particular node ends. So, so we have node 3. Node 3 dominates itself. We just looked at the definition of dominance. But node 3 does not dominate node 5. So the dominance of node 3 ends at node 3. So the next node that it does not dominate is 5. So 5 is in the dominance frontier of node 3. Similarly, for node 4, 5 is in the dominance frontier of node 4. And now we have the concept of iterated dominance frontier. So iterated dominance frontier is an iterated computation of dominance frontiers. So it's dominance frontiers along with their dominance frontiers. So for instance, we have, so for instance, we have node 5 in the dominance frontier of node 3 and node 4. Now since this was in the dominance frontier of node 3 and node 4, we placed a phi function here. And because of this phi function, we got a new definition of variable a here, which traveled back through this edge into node 2. And thus, since there was a definition of a here, we computed the dominance frontier of 5 again. And this is what is the iterated dominance frontier. So 2 is in the iterated dominance frontier of node 5. Observe that it was not in the dominance frontier, but now it is in the iterated dominance frontier. So now that we looked at these concepts, extending the notion, in order to do phi function placement at the interprocedural level, we need to extend the notion of dominance to the interprocedural level. And this needs to be done context sensitively. So as we saw, dominance uses the notion of all paths reaching a node. And for context sensitivity, we need to partition the paths based on their context. If we do not do that, we'll miss out on some useful information. So we'll look at that in this example here. So consider this example for constant propagation. Uh, Here we have this main function. It calls procedure P through this path, procedure Q from node 3, and both procedures P and Q call the procedure R. If we were to do constant propagation, we can only do constant propagation if node P so node 4 here can be optimized to print 5 using context sensitive constant propagation. We know that the values of A and B here are 2 and 3, they are 3 and 2 here, and thus this should be 5 in both cases. So if we look at this, not every path from start to this passes through node P, but not every path from start to this particular node passes through node P. But this is what would happen. In this case, we wouldn't be able to do constant propagation. But we can do this if we do the partition of paths context sensitively. So what we would do is, in the context of the call chain 2,6, that is the call at node 2, followed by the call at node 6, node 5 dominates node 9. Similarly, in the context of the call chain 3,6, the call from node 3, followed by a call, it should be 8, the call at node 8, the node 7 dominates node 9. So, going back to our problem, if we consider all paths without considering context and partitioning them based on the context, we would have to conclude that neither node 5 nor node 7 dominate node 9. And in this case, constant propagation would not be possible. And thus, we would miss out on a very important optimization. And hence, we must partition the path based on context. So this is just an intuitive description of the idea, and we need a mathematical definition for it. We also need an efficient algorithm, and to do this, there's this thing. So we are already computing reaching definitions at the interprocedural level to build cost SSA, as Dr. Pritam just said. So our idea was, why not just use these reaching definitions to perform the placement of 5 functions at the interprocedural level. So we use a modification of the reaching definitions analysis as an algorithm to compute dominance. And today we shall be talking about this at the intraprocedural level, and we further aim to extend it to the interprocedural level. So let's first look at reaching definitions analysis in a quick glance. So here's a CFG, and these are the definitions. And so we'll compute what definitions reach at which node. So at node 1, there's uninitialized definitions of A and X reaching, followed by at node 2, we have A1, X1 reaching from here, and A2 and A3 reaching from this back edge. This is followed by A1, A2 and A3 and X1 reaching at node 3, and similarly reaching at node 4, followed by A2, A3 and X1 reaching node 5. Observe that A1 definition gets killed here, so we just have A2, A3 and X1 as the definitions reaching node 5. So this is the final set of reaching definitions. And now let's look at how we can use this to perform 5 function placement. Observe that multiple definitions of A reach nodes 2, 3, 4 and 5. So intuitively, we must merge all these definitions into a single definition, just like we do for 5 functions. So we must do this to preserve the SSA property of that every use has exactly one definition reaching it. So we need to create a new definition representing the merged set of these definitions, and this should be done at the earliest point of the CFG and only once per set. And the new definitions that are created would now correspond to the required 5 functions. So now we come to the notion of augmented reaching definitions analysis, which is the proposed idea. We propose ARDA, and here we represent the conventional definitions by the notation of XNC, where N is the node number at which this definition is generated, and C denotes that it's the conventional definition. To merge the definitions when we have multiple definitions reaching a particular node, we need to create a new definition. We just said that. So we denote those definitions by the name X and A, where N is again the node number, and A denotes an augmented definition. This is done because we are naming the definitions based on the node number that they're generated in. And it's possible that in the node that we are inserting a newly generated augmented definition, a definition for that particular variable may already exist, something like x equal to x plus 1 or so. So we need this superscript to distinguish between these definitions. So this is our CFG on the left. Observe that we are now converting it into the augmented reaching definitions form. So we have renamed those definitions using our conventions C and A. Here at node 2, we had multiple definitions of A reaching. So we merged them into a single A to A definition. At node 3, now instead of all those definitions trickling down, only A to A is reaching here. Similarly at node 4. At node 5, we again have 2 definitions, so we merge them into one single definition, A5A. And thus, we get the augmented reaching definitions form that is on the, we get the form using the augmented reaching definitions on the right. So observe that we have placed 5 functions at these nodes wherever we generated new definitions, and the 5 function placement that was given by dominance frontiers that we used for classical SSA 5 function placement coincides with what we got using our augmented reaching definitions analysis. So hence we propose a theorem that an augmented definition is generated for a variable x in node n if and only if a dominance frontier of some node m that contains a definition of x. So this means that the node at which we are inserting this newly generated augmented definition is in fact the dominance frontiers in that particular control flow graph. If you need a proof, then talk to me later. We can take it offline. So what? We spoke about all these things, but is it really optimal? How do we know that? So the interprocedural placement of 5 functions is defined using dominance frontiers, and it is very well tested, verified, and used in production compilers. So it's tried and tested, and our theorem proves that the set of nodes identified by augmented reaching definitions analysis to place these augmented definitions coincides with the placement of 5 functions that has been given by the classical SSA 5 placement algorithm. So what's next? We aim to, now we've done it at the intra-procedural level. We aim to implement this, and then we aim to extend it to the inter-procedural level. We aim to, and to do this, we need to make this context sensitive. We need to define the notion of interprocedural context sensitive dominance mathematically and extend this correspondence thus to the interprocedural level. Thank you.
Any questions?
You speak well.
See, the constant propagation by definition is the traditional one is non-distributive. So now the example you showed, you said, look, I have a function called from two different branches. I will deal with it context sensitively, and hence I'll get the precise answer, right? That answer you will not get if you actually inline the function. Do you see that? If you had inlined the function there at the call sites, then you would not get this because if you set a equal to 3, b equal to 2, a equal to 2, b equal to 3, see, basically you're keeping additional information, right? Which is good. I just wanted to understand. Yeah. So here you have c equal to a plus b. Instead of c equal to a plus b, let us say I'm passing the value of a and b inside R as arguments. And R is setting a equal to 2, b equal to 3, and a equal to 3, b equal to 2. Okay, at the join point, I'm doing the sum. Using your idea, I like it. Just that you will get the 5 at the join point. And if you do traditional analysis, it will be a bottom. So it's basically you're keeping information per path. You're keeping information per path. What's the maximum fallout can happen? What overhead can you get? She seems to be tracking information per path.
For interprocedural.
But I'm trying to see it as per branch here. So I'll put the code inside a function. So I'm asking her what's her estimate of the overhead it can have, contain in terms of how many paths do you have to track? Is it linear in terms of the branches or can it go more than that?
I don't know design.
No, not linear. Let's say you have
It's a number of
nested.
value context.
No, but here let's say you have number of nested branches. Will it be still linear or can it be more than that? If you have nested branches, no difference.
Value context, same thing. Number of definitions that reach there, not the number of branches.
Number of definitions.
I mean, if you had different definitions in each branch, then that.
Then we read off.
Yeah.
Any other questions?
So let's thank the speaker once again for a very nice talk.